The Earth spins once a day. At the equator, that means you're moving about 1,000 miles per hour. Sounds fast, right? So why don't you fly off into space? Stick around. The answer may surprise you. Watch this roller. When it spins, water sprays everywhere. Newton's first law says objects keep moving straight unless a force bends the path. The water tries to go straight. The roller keeps turning under it, so it flies off.
So why doesn't that happen with the Earth?
Now let's compare the roller to the Earth. The roller spins about 8,000 times per minute. That's 133 spins per second. The Earth spins just once every 24 hours, 0.0007 RPM. So in terms of spin rate, the roller is going about 11.5 million times faster than the Earth. But here's the twist. At the edge, the roller is only moving about 20 to 30 meters per second. That's about 45 to 65 miles per hour. At the equator, the Earth's surface is moving about 465 meters per second. That's about 1,037 miles per hour. That's nearly 20 times faster than the roller's edge, and almost as fast as a supersonic jet. So the roller wins on spin rate, but the Earth wins on surface speed. Which really matters, the speed or the spin rate? Let's find out. Think about driving a car on a date. When I was a teenager, before bucket seats and when nobody wore seatbelts, we had a thing we called the benefit curve. Take a sharp U-turn at just 20 miles per hour and your date is slammed against the door. Make a nice wide turn going 80 miles per hour and your date would conveniently lean into you. Go 100 miles per hour straight down the Autobahn and your date just sits there calmly on her side of the car. See the pattern? It's not the speed that matters, it's how fast you're turning. That's what spin rate measures. The Earth spins just once per day. That's the gentlest, widest curve imaginable. Way too weak to throw you off. You can also see this with a bucket of water. Okay, here's the water. It's from the rain the last couple days.
Yeah.
Okay, if I take this bucket of water and put it upside down over my head, what's going to happen?
It's going to spill everywhere.
What?
Okay.
I know exactly what's going to happen.
What if I do this? What if I do this? I go...
What the heck? What the heck?
Okay, so why doesn't the water land on my head? Because I'm spinning it over and its centripetal force is pulling the water into the bottom of the bucket. When you swing a bucket fast, the water stays in. But if you spun it only once per day, the water would fall right out. So I'm going to put the ice in the bucket. What happens when it goes over my head upside down? Okay, we have to go slow. That's cold. Earth's spin is like that. Way too slow to fling anything off. Gravity wins. So maybe you're thinking, are you sure? I still think 1,000 miles per hour is enough to yeet you out of here. So let's do some experiments to prove if I'm right or wrong. First, let's measure gravity. Drop a D&D die from 1 meter, then from 2 meters, and then we'll record it in slow motion. So we filmed at 240 frames per second and count the frames. At 1 meter, we got 108 frames, or about 0.452 seconds. At 2 meters, we got 153 frames, or about 0.65 seconds. So the acceleration due to gravity is 2 times the distance divided by the square of the time. And it turns out our experiment confirms that the constant g, or the acceleration due to gravity, is 9.8 meters per second squared. Cool. But does Earth's spin have any effect? Yes, but it's tiny. If you put a 1 kilogram weight on a scale at the South Pole, it reads 1,000 grams. At 45 degrees latitude, it reads about 997 grams. And at the equator, it'll be about 996 grams. So yes, the spin makes you a few grams lighter at the equator, but nowhere near enough to fling you into space. Here's the math behind it. Earth's angular velocity, omega, equals 2 pi divided by the time in seconds that it takes the Earth to do one rotation, which is 86,400, which gives us 7.27 times 10 to the minus 5 radians per second. Now, centripetal acceleration at the equator equals the angular velocity squared times the radius of the Earth. So at the equator, that gives us about 0.03 meters per second squared. Remember, we measured the acceleration due to gravity to be 9.8 meters per second squared. So the force from gravity is about 300 times more than the centripetal force from the spinning of the Earth. That was a lot of math, but we can actually prove this formula just using a bicycle wheel and the accelerometer inside a phone. If you'd like to see that, let me know in the comments and we might make it into another video. So in conclusion, yes, the Earth spins. At the equator, you're moving about 1,000 miles per hour. But because it spins only once per day, the turn is so gentle that gravity easily holds you down. Gentle enough that it may make you a few grams lighter at the equator, but it definitely won't send you careening into outer space.